Welcome back to our series of lectures on chemical bonding. In today's session, we will talk about molecular orbital theory. This will be part 1 of our discussion on molecular orbital theory. The session is planned as follows. That is, to begin with, we will briefly review the contents of previous sessions. Thereafter, we will try to establish the inadequacy of valence bond theory. That is the theory which we discussed in the previous session. Having done that, we will outline the approach of molecular orbital theory, that is the today's session, and thereafter, having laid down the approach of molecular orbital theory, we will see that how do we use this theory to kind of describe bonding in homonuclear diatomic molecules of first and second periods. Then towards the end, we will sum up what we do in today's session. So, with this outline, let us make a beginning by recalling what we have done so far in this series. What we have done so far is, we started by introducing the concept of chemical bonding with the historical perspective and discussed the classical theories of chemical bonding, wherein we talked about the Causal's theory and Lewis theory and things like that. Thereafter, we explained VSEPR theory and used it to predict the geometry of different molecules. Having done that, we moved on to discussion on valence bond theory and outlined its limitations. Then, in this context of limitations, we brought in the concept of hybridization, discussed about it, and then saw that how do we use it to explain the geometry of molecules. So, that is all what we have done so far. It will be worthwhile to recall that according to valence bond theory, the valence atomic orbitals with unpaired electrons overlap to form a bond. That is, as per the valence bond theory, bond formation basically involves pairing up of orbitals with their unpaired electrons in them. And in this process of pairing up, there is some kind of an accumulation of electron density in the internuclear region, and this accumulated electron density is the one which holds the two nuclei together, and we say a bond is formed. That is the valence bond approach to chemical bond formation. Another thing we have done, we have realized in the previous session was that this theory, the valence bond theory, works fairly well for diatomic molecules, but when we have to talk about the geometry or the bonding in case of polyatomic molecules, we have to bring in the concept of hybridization. Okay. So, that is what we had in case of VBT. Now, let us go further and see that in what way is valence bond theory inadequate, and that we try to establish with the help of an example of bonding in the case of oxygen molecule. We know that the electronic configuration of oxygen atom is 1s2, 2s2, 2p4. That is how do we represent that. This helium core represents the 1s2, and then we got 2 electrons in the 2s orbital, and then there are 4 electrons in the 2p orbital there. When 2 atoms of oxygen, they have to bind to each other. So, what kind of bonding is possible is that one of the 2p orbitals, that happens to be say 2pz orbital, that is the one which is oriented along the internuclear axis. So, the 2pz orbitals, that is the of the 2 oxygen atoms, they combine together. This is 2pz orbital of one oxygen atom, this is that of second oxygen atom. The two combine, they overlap here and they form a sigma bond over there. So, that is one bond formation. The second bond formation takes place by the lateral overlapping of py orbitals. Py orbitals are oriented in a direction perpendicular to the pz orbitals there. So, when they overlap laterally, once again we find that is a pi bond formation there. If you put the two together, we find that in case of oxygen molecules, there are 2 oxygen atoms over there, 2 oxygen nuclei here there. This is one pair of electrons here, which is due to overlapping of 2 pz orbitals, and this is because of the py orbitals there. We find that in this representation, all the electrons are paired up. As a consequence, we expect this molecule to be diamagnetic in nature. That is a basic premise what we have for the magnetic behavior of molecules there. However, what you find is that experimentally oxygen is observed to be paramagnetic in nature, and that paramagnetic nature of oxygen is established by using liquid oxygen. If you take liquid oxygen and pour through a magnetic field, we find that this is held by the magnetic field. That means, it is attracted by the magnetic field, and that is possible only if it is paramagnetic in nature. Had it been diamagnetic, it would have flown smoothly through this without getting held up into the magnetic field over there. So, theoretically speaking, according to valence bond theory, we expect oxygen to be diamagnetic. Experiment tells us that oxygen is paramagnetic. So, there is a mismatch there, and we need another theory which can kind of accommodate this experimental fact regarding the magnetic nature of oxygen molecule. And that theory happens to be molecular orbital theory. Is a quantum mechanical approach to chemical bond formation like valence bond theory. Valence bond theory based its approach onto the quantum mechanical behavior of atom, that is, we talked about the concept of orbital and things like that. Same thing holds over here also. We will talk more about it as we proceed. Now, this theory was proposed by Robert Mulliken and Friedrich Hund in around 1927, and for this work Mulliken was awarded Nobel Prize in 1966. The basic premise of this theory goes as follows, that is, the atomic orbitals of the constituent atoms combine to generate new types of orbitals called as molecular orbitals. That is, what happens is here, you have got two atoms, atom A and atom B, the two have to bind together. For that to happen, what this theory proposes is that these two orbitals, say of atom number 1, atom number 2, they come close, they overlap, they mix together and they generate new orbitals which are called as molecular orbitals, and those molecular orbitals are spread over or delocalized over the whole molecule. Now, let us try to contrast this with what happened in case of valence bond theory. In case of valence bond theory, what we had was atom A comes, atom B comes, two atoms come together with their corresponding valence orbitals, the two orbitals overlap and there is an accumulation of charge density here, and this accumulated charge density is responsible for the bond formation. On the contrary, in case of molecular orbital theory, what we have is the two atomic orbitals come together, they combine together to give you new molecular orbitals, and those orbitals are such that electron does not confine to one region here, the electron is kind of available over the whole molecule across all the nuclei of the molecule there. So, that is valence bond theory gives you a localized view of bond formation, whereas molecular orbital theory gives you a delocalized view of this. In that sense, the two theories are different. Otherwise, both of them use the quantum mechanical formulation about the atomic structure there. One more thing we have to keep in mind here is, as I was just mentioning, we talked about the localized and delocalized bonding there. You remember that when we talked about valence bond theory, we talked about hybrid orbitals, and when hybridization takes place, in case of hybridization, the atomic orbitals of only one atom participate, and then they give rise to the hybrid orbitals which belong to that atom by itself. On the contrary, when you talk about molecular orbital theory, in case of molecular orbitals, the two atomic orbitals are different atoms combined together to give you molecular orbitals which belong to the whole molecule. So, these are 2 points of differentiation between the valence bond theory and molecular orbital theory. Okay, let us move further. Now, with this basic premise, let us see how do we go ahead over this. Remember, when we talked about atomic structure, or we talk about energy levels in atoms there or different orbitals there, we take hydrogen atom as the basis there. So, because hydrogen atom is the simplest possible atom there. So, we talk about the structure of hydrogen atom, and then on that we built up the structure of all other atoms over there, the polyelectronic atoms over there. Similarly, when we talk about molecules, the hydrogen molecule ion is two nuclei, that is two protons and one electron. That is the simplest possible molecular system we have. So, that plays the same role in understanding the molecular structure as is played by hydrogen atom in case of atomic structure. So, hydrogen molecule ion is the simplest possible molecule we can think of. Now, when we talk about molecule formation in the context of, say, molecular orbital theory, and we take hydrogen molecule ion to be the simplest possible system. So, how do we go about this whole thing is, that is, we try to formulate the Schrodinger wave equation for that and solve it to calculate the energies and shapes of different molecular orbitals. But even with such a simplest possible system, we find that the Schrodinger wave equation for even hydrogen molecule ion cannot be solved. Since the Schrodinger wave equation cannot be solved, so what do is we take recourse to approximation. That is, we do not formulate a Schrodinger wave equation and solve it explicitly. As against that, we used a common logic and an approximation approach. By that approximation approach, we try to formulate or generate molecular orbitals there, and that approximation is called as linear combination of atomic orbitals, or commonly it is called as LCAO approximation. Use molecular orbital theory to understand chemical bonding in different kind of molecules. The approach is as follows, that is, as a first step we construct the molecular orbitals by combining the available atomic orbitals, and we use LCAO approach for the purpose there. Thereafter, we accommodate the electrons provided by constituent atoms. Suppose there are two atoms 1 and 2, we take the atomic orbitals of these two atoms there, put them together, generate the molecular orbitals, and then thereafter the number of electrons in this and this, the two are added together, and those number of electrons are distributed amongst these energy levels over there, which are the molecular orbitals there. And in the process of distributing electrons along this kind of molecular orbitals, we have to adhere to the Pauli's exclusion principle and Hund's rule of maximum multiplicity, as we did in case of atoms there. Now, let us see how do we get molecular orbitals using LCAO approximation. For this to be done, what we do is we take atomic orbitals of the two contributing atoms and combine them linearly. And the basic requirement for this to be taken up is that the combining atomic orbitals should have comparable energy. That means, when you take atom 1 and atom 2, if I want to combine the atomic orbitals, these three conditions have to be met there. That is, the energy of this atomic orbital and this atomic orbital should be comparable. I cannot combine one atomic orbital of a given energy there, another of very high energy there. The two are, this is not permissible, they will not lead to a reasonably good acceptable molecular orbitals there. So, that the first requirement is that the energy should be comparable. Second is they should have similar symmetry over the molecular axis. Typically, the molecular axis is taken as a z axis. And third expectation is, that is, when the overlapping takes place, it overlaps to the maximum possible extent there, because higher the overlap, we are going to get a stronger bond over there. And another thing what we will be observing is that when we take n atomic orbitals, I mean, suppose I take 2 atomic orbitals, I will get 2 molecular orbitals. If I take 4 atomic orbitals, I will get 4 molecular orbitals. That is, the number of molecular orbitals generated will be equal to the number of atomic orbitals which are participating in the linear combination process there. Okay. Now, I think with this background, we are equipped to move further and take up the homonuclear diatomic molecules of first period. That is, we will talk about how do we use molecular orbital theory to explain bonding in homonuclear diatomic molecules of the first period to begin with. Now, let us see, we take the again a very simple molecule there, we take hydrogen molecule. Now, to understand bonding in that, in case of hydrogen molecule, we know that hydrogen atom, the two hydrogen atoms are going to combine together, and hydrogen atom has got 1s orbital. So, what we do is we take 1s orbitals of the two hydrogen atoms and combine them to see what kind of molecular orbitals we get there. So, these are the two atomic orbitals. This is say 1s orbital of atom 1, 1s orbital of atom 2. The two will combine together. Now, when you do linear combination, the two contributing atoms atomic orbitals can combine constructively or destructively. When they combine constructively, that is, say this plus this, that means this is an additive combination there, we find that the resulting molecular orbital looks something like this. That is, we have got 2 nuclei here and there is an electron density which is spread over the whole molecule. We can see that in this case the orbital is confined to atom here, here we got the electron density along the whole molecule over there, across both the nuclei over there. So, this is one kind of an orbital what we get as a consequence of constructive overlap of the two atomic orbitals. If there is a destructive overlap, that is this minus this, what you find is we get molecular orbitals of this kind there. So, these are the two nuclei and we find that possible electron densities are oriented as shown over here, that is into the internuclear region there we find that the electron density goes to almost 0. Now, we find that two atomic orbitals are combining, we are getting 2 molecular orbitals. That is first and foremost thing what we observe when we generate molecular orbitals by using LCAO approach there. This orbital, the first one here what we got here, because of the kind of constructive overlap between the two, is called as a bonding molecular orbital. It is called as bonding molecular orbital because we find that there is a increased kind of electron density in the internuclear region there. The two nuclei are held together there. As against that, this orbital is anti-bonding, because in this case there is no electron density in the internuclear region there. Going further, this orbital is given a symbol sigma 1s. Sigma stands for, this is a type of bonding, it is called a sigma bond. Sigma bond will be formed when the two atomic orbitals are kind of combining along the internuclear axis. So, that will be a sigma bond over there. So, this also is obtained in the same fashion. So, this also has a designation as sigma there, and this subscript of 1s indicates that is the 1s orbitals are involved in the formation of molecular orbitals, and here we find that this is sigma 1s, this is sigma star 1s. This star indicates that we are talking about an orbital which is of this type, which is anti-bonding. Bonding molecular orbital, there is no superscript over there. For anti-bonding, we have a star as a superscript there. So, there are a lot of things in this particular kind of representation I am showing you. We have to understand all these terms as we move further. Okay. Now, so let us look a little into what are the bonding molecular orbitals. Bonding molecular orbitals, as I just mentioned, they are obtained by constructive overlap of the atomic orbitals, number 1. Number 2, the electron density is concentrated between the two nuclei, as I just showed you. Thirdly, these molecular orbitals have got energy lower than that of the contributing atomic orbitals. We saw that atomic orbitals having certain energy there, molecular orbital has got energy lower than that, whereas antibonding has got energy higher than that. And the electrons occupying these orbitals cause bonding, because when we said that the basic approach of molecular orbital theory is that we construct the molecular orbitals first and then we fill in the electrons in that. So, any electron which occupies a bonding molecular orbital is going to contribute to the bonding, or it will increase the stability of the molecule there. On the other hand, the antibonding molecular orbitals are the ones which are obtained by destructive overlap of the atomic orbitals there. And we find that in such cases the electron density between the two nuclei is reduced to almost 0, because the two wave functions which add destructively actually they cancel each other. As a consequence, the electron density happens to be 0. There is a node in that place there. The third observation is that contrary to what we had in case of bonding molecular orbital, in case of anti-bonding molecular orbital, we find the energy is more than that of the contributing atomic orbitals. And lastly, any electron which occupies an anti-bonding molecular orbital is going to decrease, cause decrease in the bonding or decrease the stability of the resulting molecule if it is formed there. So, that is the two kinds of orbitals we have got there. Now, let us go a little further and see that how do we represent this in terms of a diagram. We have seen there that by using LCAO approach, how do you get the molecular orbital. So, how do you get them? We combine them constructively or destructively, and as a consequence of that we get molecular orbitals of bonding nature and of anti-bonding nature. Bonding are low energy, anti-bonding are of high energy there. But how do we represent all that in terms of a energy level diagram? Let us look at it. So, when I have a hydrogen molecule, for hydrogen molecule, so this is a typical picture you must have come across. This is called as a molecular orbital energy level diagram. So, what we show here in this diagram is we show these are the energy levels. This is atom number 1, this is atom 2. So, this is 1sh, 1sh. There are two atomic orbitals which are combined together to give you the molecular orbitals there. So, the central streak here represents the molecular orbitals, and on the left and right we represent the contributing atomic orbitals there. Okay. So, in case of hydrogen molecule, as we just saw, that is when 1s orbital of this atom 1 and atom 2, when the two combine together we get a molecular orbital there. So, this was sigma 1s as we showed you earlier. So, this is the bonding molecular orbital and this is the anti-bonding molecular orbital. Bonding molecular orbital has energy less than the contributing atomic orbitals, and this has got energy more than the contributing atomic orbitals there. That is one. You see that in the brackets we have given some other notation there. This is 1 sigma G, this is 1 sigma U. So, this G and U have something to do with the parity of the molecular orbitals we generate. We will talk about it in a short while from now. Let us go further into this and see that if this be so, because we said that in case of molecular orbital theory, we generate the molecular orbitals and then fill the electrons in them. So, in case of hydrogen molecule, we got only 2 electrons, one for atom 1, one for atom 2. These 2 electrons, when you try to fill into these molecular orbitals, both of them will be occupying the sigma 1s orbital there, because first electron will come here and second can be here or here. It cannot go there because energy is too high, it will be pairing up over here. So, what you get is we get 2 electrons in this orbital there. So, as a result of this, we can write the molecular orbital configuration as sigma g to sigma u 0 over there. Okay. So, that is both the electrons are occupying the 1 sigma g orbital there or sigma 1s orbital, as we use this notation or this notation. So, I am sure that you must be realizing that this all is running parallel to what we have in case of atoms there. In case of atoms, what do we have? We got atomic orbitals, and in atomic orbitals we fill the electrons according to the Pauli's exclusion offer principle, Pauling's rule and Hund's rule there. And then what you get is we get a electronic configuration there. Here we are getting a molecular orbital configuration there. Before we proceed, let us understand the meaning of this term G and U and also the types of orbitals we found there. So, when we talk about the molecular orbital types there, we said sigma orbital, sigma MO. What does it mean? Let us understand this. Sigma molecular orbitals are obtained by atomic orbitals combining along the internuclear axis. Let us take examples here. This is what we just saw right now. Two 1s orbitals, they combine together along the internuclear axis, they give you a sigma orbital over there. Another possibility could be a 2p z orbital of atom 1 and 2p z orbital of atom 2. The two combine along the internuclear axis, they generate this kind of a molecular orbital. This also will be called as a sigma molecular orbital, because this is coming as a consequence of overlapping along the internuclear axis. Typically, all such orbitals will have cylindrical symmetry around the internuclear axis. If we look at this internuclear axis here, if you look around that, so it is symmetrical around the internuclear axis, the orbital will be symmetrical here. They are the sigma orbitals there. And if you look along the internuclear axis, say if I look from this side, we find that typically they look like s orbitals. So, s from s it has come as sigma there. The second possibility is that we can have pi molecular orbitals. Pi molecular orbitals are obtained by sideways combination of atomic orbitals. It may happen, we will come to this as we proceed further, that is say 2py orbital of atom 1 and 2py of atom 2. The two combine together. So, when the two combine together, we find that their orientations are in a direction perpendicular to the internuclear axis. So, these orbitals will be overlapping laterally, they will combine laterally, and when they combine laterally, we find this is the kind of molecular orbitals we generate there. Such molecular orbitals are called as pi molecular orbitals there. They look like p orbitals along the internuclear axis. I mean, if I see from this side, they will look something like a p orbital there. So, there are two types of molecular orbitals which will be coming across, sigma orbitals when there is a overlapping or the combination along the internuclear axis, and pi molecular orbitals when the combination is lateral in a direction perpendicular to the internuclear axis there. The second thing which we just mentioned in the previous kind of representation, we found out that we talked something about the parity of the molecular orbitals there. Let us understand that. Parity basically refers to, so these are two kind of molecular orbitals I am showing over here. So, here we have got plus plus here, we got plus and minus over there. Now, what does it mean? Let us understand that. Now, if I basically when you talk about molecular orbitals, they essentially are nothing but wave functions there. If it so happens that is the wave function of a molecular orbital what we got there, this remains unchanged under inversion through the center of symmetry. That is, if I got this molecular orbital there, this is center of symmetry of the molecule there. If I invert it, so the wave function does not change. If it does not change, we call it as even function. The parity happens to be even, and it is called as G rate, and that is why the symbol G is there. The sigma 1 sigma G, that G comes from here, because that molecular orbital what we got there was of this type. That is, it was symmetric when it was inverted through the center of symmetry. It remained unchanged on inversion through the center of symmetry there. On the other hand, if it so happens that the wave function is changes, that means the plus becomes minus and minus becomes plus. If we invert through center inversion there, then this molecular orbital is called as the odd molecular orbital or ungirate, and given a symbol as u. We had sigma 1 sigma u as a notation over there. Okay. Now, there is one more thing we need to talk about, that is called as bond order. Bond order basically is a measure of the stability of molecule, and it is defined as half of Nb minus Na, that is Nb refers to the number of electrons in the bonding molecular orbitals, and Na happens to be the number of electrons in the anti-bonding molecular orbitals there. Now, if we see that if it so happens for a given molecule the bond order comes out to be 1, that means there is a single bond there. If it is 2, it is double bond. If it is 3, it is a triple bond there. So, that is the meaning of bond order. How many bonds are found between the two corresponding atoms in the molecule there. And if it so happens that the molecule contains an odd number of electrons, we will find that the bond orders could come out to be 1 by 2, 3 by 2 or 5 by 2 and so on and so forth. Now, for the bond order of the molecule we just talked about, that is hydrogen molecule, we find that both the electrons are in the bonding molecular orbital, there is nothing in the anti-bonding there. So, it is 1 by 2, 2 minus 0, that comes out to be 1. That means, the bond order of hydrogen molecule is 1, that is the two atoms in hydrogen molecule are bonded by a single bond. That is the meaning of bond order. We will talk more about it as we move further. Okay. Now, if what happens, does helium molecule exist? Let us have a look at it. To understand that, what do we do is, because helium also belongs to the first period of periodic table. So, what do we do is, for it will have similar kind of molecular orbitals as we have in case of hydrogen molecule there. So, you see that the molecular orbitals are identical to what we had in the case of hydrogen molecule. But in this case, if helium 2 is possible, it should have 4 electrons, because each helium atom has got 2 electrons. So, 2 atoms will combine together, the total number of electrons will be 4. When you take the 4 electrons and fill into this molecular orbitals, we find that the configuration comes out to be 1 sigma G2, 1 sigma U2, that is 2 electrons in the 1s orbital, the bonding molecular orbital, and 2 electrons in the anti-bonding there. And if you compute the bond order, it will come out to be 0, and that means according to molecular orbital theory, helium 2 molecule does not exist, and it does not exist, we all know that. Okay. Let us move further. What about helium molecule ion? Helium molecule ion will be 2 atoms of helium put together and 1 electron is lost from there. So, this will be total of 3 electrons there. So, in this case, our molecular orbital energy level diagram will look something like this. That means, there will be 2 electrons in sigma 1s orbital there, and there will be 1 in the sigma star 1s orbital there, and the corresponding molecular orbital configuration will be something like this, and the bond order will be 1 by 2. That means, we find that helium molecule ion has some stability there according to molecular orbital theory, and what it implies to say is that He2 plus ion is more stable than a helium atom and a helium ion put together there. That means, they do come across, they do come close, and they do come into some kind of a coexistence in the form of a molecule ion there. So, helium 2 as a molecule does not exist, but helium molecule ion can exist according to the molecular orbital theory. Okay. Now, let us move further and talk about homonuclear diatomic molecules of the second period. What we just talked so far was the first period, that is hydrogen and helium. Now, let us move further and take up homonuclear diatomic molecules of second period, and in the second period what you find is that if you look into the diatomic molecules, you find that we can kind of distribute them or divide it into 2 groups. The first group is the one for the atoms which have only s orbitals in the valence shell there, and the second possibility is the atoms having s and p orbitals in the valence shell there. Here we will have lithium and beryllium, and here rest of the atoms of the period will come over there. And when you talk about the atoms having s and p orbitals in their valence shell, we find that there is a further possibilities, and that we may have a situation where s and pz orbitals can undergo some kind of a mixing there, and another possibility will be when the two cannot mix, they do not mix there. So, we will talk about these detailed things in the next session over there, but for now let us take up the first part of it here, That is, we talk about the molecular orbital theory of the diatomic molecules of second period, wherein the atoms only have got s orbitals in their valence shell. Let us go further. When we talk about having only s orbitals in the valence shell, we find that lithium and beryllium qualify this, because they are the only ones which have got 2 s orbitals, and the 2 s orbitals of lithium and beryllium will combine as follows. Now, you remember that this is a picture very similar to what we had in case of hydrogen molecule there, because in case of hydrogen molecule we had two that is, we had 1 s orbitals or 2 hydrogen atoms combining there. Now, what we have is we have got the 2 s orbitals of lithium or beryllium combining together. So, the story goes in the same way, we get one bonding molecular orbital, we get anti-bonding molecular orbital, and the designation will be sigma 2s here. There we had 1 s, now we have 2 s, because the contributing atomic orbitals are 2 s atomic orbitals there. That is the only difference, otherwise the story remains the same, that is the 2 atomic orbitals, that is the 2 s orbitals of lithium or beryllium, they combine together to give you 2 molecular orbital. One is a bonding molecular orbital, one is an anti-bonding molecular orbital, and since the 2 are combining along the internuclear axis, you are going to get sigma bonds over there. So, this is a bonding, this is anti-bonding sigma orbitals there. Okay. Now, with this let us go further and see, if you want to talk about the formation of lithium molecule, what kind of a molecular orbital energy diagram we will have. So, in this case, if I look at lithium, lithium is 1s2 2s1, that is there are 2 electrons in the 1s orbital and there is 1 electron in the 2s electron there, 2s orbital there. So, this the lower picture, the lower part of the picture here shows you the bonding of 1s orbitals, that is, this is 1s of lithium, 1s of lithium 1, lithium 2, the 2 combined together, you get sigma 1s, you get sigma star 1s, and the same identical picture what we had in case of hydrogen molecule. But we are more interested in this part of the picture here, wherein the 2s orbital of lithium 1 here and lithium 2, the 2 combined together to give you sigma 2s and sigma star 2s. And now, when you talk about the filling of electrons, we can talk in 2 ways. Total number of electrons in lithium are 3, the 2 atoms put together, total electrons are 6. So, they will be filled like this 2, 4, 6, that is one way of doing it. Second way is that you forget about the inner core over there, because if you focus attention only onto the valence electrons, the valence electron in case of lithium atom is just 2s1, that is 1 electron there. For the 2 atoms, total number of electrons will be 2. So, those 2 electrons are occupied by this orbital over there. So, with this we can write down the molecular orbital configuration as sigma 1s2, sigma star 1s2 and sigma 2s2, sigma star 2s0. That means, we write, one option is that we draw this kind of picture. As against that, an equivalent expression can be done by the following representation there. So, this writes that how are these 6 electrons of the molecule distributed amongst the different molecular orbitals there. And with this, we can try to work out the bond order. The bond order will come out to be, for lithium 2, this will be 1 by 2, 2 minus 0, because there are 2 electrons in the bonding molecular orbital and 0 in the anti-bonding there. So, that is one way of doing it, or we can do it 4 minus 2 by 2, once again it will come out to be 1. That means, if we add this, because these 2 are going to nullify each other, 2 minus 2 is going to make it 0. Effectively, this core is going to contribute 0 to the bond order there. So, whether you compute by using just this or all of it put together, you get the same outcome there. The meaning of that outcome is that Li2 molecule does exist, and they exist as a molecule of this kind, because bond order comes out to be 1, that means there is a single bond between the 2 lithium atoms there. Now, what about beryllium 2 molecule? Well, that means, if I take 2 atoms of beryllium, will they combine to give me a molecule or not? Let us have a look at it. I do not have to do all over the whole exercise over again. I know that when the atomic orbitals of this kind of atoms combine together, what molecular orbitals are obtained there. Once I have obtained that, then I have to just put in the electrons into the molecular orbitals and see what is the configuration, and then from there we compute the bond order over there. So, for this, the energy level diagram for Be2 will look something like this, and I am sure that by now you know how to do that. There will be a total of 8 electrons, so 2, 4, 6, 8, or if we talk about the valence electron, there are only 4 of them. So, 2 are here, 2 are here. and from this we can write down the electronic molecular orbital configuration as we did in the previous case. So, all this you write the orbitals there and write the corresponding number of electrons in them, and from this we compute the bond order, it comes out to be 0 there. So, there are 2 in the bonding, 2 in the anti-bonding. I am focusing on this part of the representation here, and that means beryllium-2 does not exist. But what about beryllium-2 ion? Does it exist or not? I am sure that we do not have to spend much time on this, because we did a similar exercise in case of He2 plus ion also. Parallel to that, we find that will be the molecular orbital configuration, because there will be a total of 7 electrons in the molecule, and the corresponding bond order will come out to be 1 by 2, because there are odd number of electrons there, and we find that beryllium-2 plus ion, beryllium-2 ion is a stable species. It does exist, can exist there. Okay, let us sum up what we have done today. What we have done today is we reviewed the contents of the previous sessions. Thereafter, we established the inadequacy of valence bond theory. We established that valence bond theory fails to give a picture of oxygen molecule which is in agreement with the experimental observation of the fact that oxygen happens to be paramagnetic, because valence bond theory predicts it to be diamagnetic in nature. Having done that, we outlined the basic approach of molecular orbital theory, and then we explained bonding in homonuclear diatomic molecules of first and second period atoms there, and using molecular orbital theory, and herein we focus attention only on to some of the atoms there, and rest of it will be taking up in the next session there. Okay, thank you.